sure more will straggle in over the next minutes.
No worries. We can start in a few minutes more.
Yeah.
It's fine. I'm just standing up because I don't want to be. I've been sitting the whole day.
Oh, yeah.
I'm thinking about taking a boat.
Have you ever gone to Egypt?
Oh, yeah, I've been there.
Yeah.
Yeah.
That is amazing. Some of these temples.
Yeah. In fact, I think 3 times in a row, I was gonna take the Nile cruise.
Yeah, I took them out for
3 times they were canceled. And I had to scramble, change my itinerary around. So I wound up going to Dubai and the bikes. Oh, then I then I wound up in Italy after that. No, so I was gonna go to Istanbul. And this is for example, it's $15,000 for a short flight.
nah.
15,000. So I got to like you go to this airport, it's really cheaply. People fly into it.
Okay, are we ready? First lecture of the year.
Already?
Yes.
Wow. Nice.
I'll just stand here. You obviously grab the stage in a little bit. Thank you for coming tonight. So glad to have you here. Welcome to San Francisco Amateur Astronomers. I'm Jason, the speaker coordinator. Very happy that I called her doctor earlier, but no, I'm not a doctor yet, but well on her way. Bernie Ried Guachalla?
Guachalla.
Guachalla. Oh, I did
It's
not get it
fine.
right. Is working in, working with some of the same people that I've also rubbed shoulders with in the past, and I was really excited to over lunch, and also Dr. Mary Barsoni was with us also. We just had a wonderful lunch or dinner conversation about some of the overlap. Really fascinating. Can't wait to hear more about her. She, among other things, has helped detector and camera characterization for the Vera Rubin telescope, which is fascinating. Also helped lobby against a industrial complex going up near the telescopes, the observatories in Chile, and she succeeded in that. So some wonderful stories. Whether or not we'll get to those tonight or not, I don't know. But we are very, very happy to have you here. Honorary Dr. Bernardita, Ried
Can you listen to me?
Yeah.
Okay, great. Thank you for the invitation. Yeah, my name is a bit weird. I'm from Chile, that's why. And as you know, we use 2 last names. Hi, we just started, so you haven't missed anything. I'm not a doctor yet. I will be in a couple months. I'm really excited because I'm advancing in my PhD. As I said, I'm a PhD candidate at Stanford, working on cosmology, and in particular in observations. And indeed, I worked only for a bit on a camera, so I'm not an expert on the Rubin camera, but I'm more than happy to talk about that experience and what we learned in that study. But today I wanted to talk about the state of the art of what is part of the study in cosmology. So cosmology is the branch of astronomy that, as you're all experts also, because I know many of you are interested in astronomy, and you might know that cosmology aims to answer questions such as what is the origin of the universe, how it has evolved, what are the components, and what will happen to it. And I wanted to start this presentation with these cartoons that are closed. By the way, if my English is not good, as I said, I'm not native in English, so I might ask for your help at some point if I mix some words, but I'm starting with this closed curtains because I wanted to show you this cosmic silhouettes and tell you how much we can learn from galaxies but by using a backlight. So if I open the curtains, we found stars and galaxies that are in the foreground of what I would explain in a second is the earliest light of the universe. I don't know, where should I stand? Let me just move some stuff here. Okay, I think this is better. Is it getting, whoop, okay. So I'll be explaining why did I decided to call my talk like this and why backlighting galaxies is actually a really good way of learning from them. I always start my talk, especially because I like cosmology, traveling through space, and in particular leaving the Earth. So this is an animation. If we go into a space shuttle and we just leave, we find our moon and then neighboring planets in the solar system, then our sun, and eventually we start finding other stars. These are the stars that are our neighboring stars. Their light takes some years to reach us. And then if we go farther away, we find way more and more stars. And then eventually, not only stars, a lot of dust and gas, and I'll be talking about that, so those spots there. And then we eventually leave our galaxy. Our galaxy is mainly composed by those components, and also, I'm more than happy to talk more other components that are dark. Then we have neighboring galaxies, and then when you further move back, you find much more galaxies. In our galaxy, there's an estimate that we have approximately 100 billion stars. That's the order of magnitude. And there's also the same order of magnitude of galaxies out there. So chances of having, planets with life, of course, is high if we think about statistics. But I'm not going to be talking about life in other planets. I'm going to be mainly talking about, these amazing images that we have. This is a real image. This is taken by the Rubin Observatory, which I thought I mentioned somewhere, but at least I'm mentioning it loud. This image is mainly showing more or less how deep the Rubin Observatory is going to be observing. For context, this is a telescope that just started operating from the north of Chile. I'm going to be talking about a lot of Chile because I'm a fan of Chile. I'm from there. But I want to highlight that almost every dot in this image corresponds to a galaxy. There's only a few exceptions, in particular, the ones that have this pattern, like cross patterns, correspond to stars. Most of the rest correspond to galaxies. And you can highlight these really big ones, but these tend to be closer, but almost every dot here corresponds to a galaxy. Even though this is a static image, things are moving. And in particular, this is a simulation, it's not real. When we observe farther and farther away galaxies, we start to see they're moving farther away from us. And that's what we call the universe is expanding. If there's nothing special in Earth, if we, get away from this idea of anthropocentrism, we can, if we're not in a special part of the universe, we can argue that the observable universe, in other words, wherever we can see, things tend to be moving away from each other, and in particular also moving away from us. And this is a classic image that people show in this field. Again, it's cosmology. And usually people explain it from left to right. So there's this hot Big Bang that I'll be talking more in a second. There's a really rapid expansion called inflation. Then there's this weird thing here that has crazy colors. I'll be talking more about it. Then there's darkness. And then the first stars form, first galaxies too, and then we find the universe as we know it. But the important thing about this image is the curvature you find across time. And as you can see, this is always increasing, and that's what we call the universe's expansion. But rather than going through the arrow of time, I want to do an exercise with you, and I want to go the other way around. So instead, let's try to tell this same story, but instead of going, as I said, through time, just go back in time. We invert it. If we do that, we can do the following exercise. If everything is moving away from everything, meaning there's an expansion, in the past everything was compressed. So if we do the same exercise, if we compress the whole universe, what will happen is a similar effect that I'm showing in this box. You have particles bouncing, and when you compress this box, particles are going to bounce more. And one of the main effects you will see is that the pressure goes up. because I am compressing the same amount of matter in a smaller volume. Pressure will go up. My particles are bouncing more the faces of this box. But also, when things go higher pressure, as you remember, if you like cooking, you will know that in your kitchen, if you have these high pressure cookers, you can really reach high temperatures. So if you increase the pressure, if we compress the universe, we should expect it to increase its average temperature. So, if I compress the universe, the pressure would go up. Because the pressure goes up, temperature goes up too. And things that get hotter tend to bright. So, if we heat, for example, a metal to really high temperatures, eventually, as you have seen in the movies or in person, you have seen that when you reach really high temperatures, thousands of Celsius, sorry, I work with Celsius, but I guess it's also a lot of Fahrenheit, these metals will glow. So if we do that exercise, okay, if I compress the universe because I'm going back in time, temperature would rise because pressure would rise too, and then finally, at some point it will be so hot, if I really, really compress the universe, that I should expect it to bright. And this is what people thought in the 60s. Physicists were like, seems interesting. And in particular, if we compress the universe 1,000 times more or less, what will happen is that the temperature will go up from minus 270 Celsius up to 3,000 Celsius. I have no idea how much that in Fahrenheit, but it's really low temperatures. Like if you really literally go out from our galaxy, extend a thermometer and try to measure temperatures out there in the universe, you will measure really, really low temperatures. A few Kelvin degrees, 2.7 approximately. So the exercise we can do is okay, if we compress it up to 1,000 times, the temperatures should increase, as you can see, a couple of orders of magnitude. So it can be really hot. And that temperature in particular, all the particles that you collapse, you should expect them to be emitting light too. Same exercise as I said. If we increase the temperature of a metal, you would expect at some point to increase the temperature and bright. And in particular, if we compress the universe and we do this calculation, we should expect that at that temperature, the universe should be bright. And in particular, that's true, and that's actually more or less if you go and buy a light bulb, you will see that there are different temperatures in Kelvin. And in particular, if you have 3,000 Kelvin, which is more or less the color I try to show here, but this screen is not helping that much. But what I just want to say is that in theory, if you grab all the contents of the universe and you compress it, in theory, you should expect the universe to bright at this temperature. So, what people did, this is actually visible light, right? But as I said, the universe then, we compress it, but in reality, if we follow time, the universe should expand. And what happened in a universe that is expanding is that light gets stretched. So if we have a galaxy there in the left, and the universe is expanding, the space between us, observers, and that galaxy is growing through time, the light traveling through that space will extend like an accordion. That's how I try to explain it, but in simple language, the wavelength will increase, and the frequency will go down. So back in the 60s, this physicists were thinking, if we believe that the universe was glowing at that temperature, and was visible light actually, we should expect that to get stretched through the universe. And in particular, I really need to use this diagram to explain what temperature that light reaches. Here we have the electromagnetic spectrum, so the different frequencies that you can have of light. You're all astronomer passionate, so you know about these things. You know that we observe in the visible. But if you go to lower frequencies, you will have first infrared, microwave, and eventually radio. So if the universe expands 1,000 times, remember we have compressed it 1,000 times, so now we're expanding it 1,000 times. Visible light will turn into microwave. And microwave could even be like a couple of nanometer, 0.1 centimeters. So really like scales that are, we're more used to. We're not that used to this like measurements, but these are actually things we can understand more as humans. And in particular, the temperature would decrease up to the temperature we measure when we extend our hand outside of the galaxy and we measure the temperature. And I said microwave, but wait, microwave like the microwave of my house? Yes. A lot of people are not aware that microwaves, they're not like ovens that are like, heating everything through this is a different system, right? We're not like, turning fire, or what we do in microwave is that literally when you put your food in the microwave, you have light that is in that frequency that is really good at breaking the molecules of water, and that's why your pizza is really bad in the microwave. So water and microwave are really good friends. They like to dance together. That's why I recommend you to put your pizza with a glass of water. I don't know if it works, but at least the pizza is better in my opinion. But yeah, the microwave like your home. And in particular, back in the 60s, when they first observed this light, they found this. This is the light ever emitted by the universe when it was in its first stages. And the first thing you will realize is, well, first, why it looks like an egg. Well, this is a 2D image of the whole space, first thing. Second thing, that line in the middle is the Milky Way. The Milky Way is also emitting, but in cosmology, with all the respect to my colleagues, we don't care about the Milky Way. We care about extragalactic stuff. So, this is the image observed in 1964 by Penzias and Wilson in Princeton when they turn on their antenna. I'm more than happy to talk about that story because it's actually funny. Because of time, I'm just going to skip it. Or you want me to tell it? Okay, I'll tell you. There were, I have some slides at the end. Maybe you can just jump. You're a small audience, I could just be informal, I guess. No, I erased them. Damn. Sorry. Oh, this is all recorded, it's so embarrassing. Yeah, so the story was that Penzias and Wilson in 1964, they were working on the Bell Labs, and they were developing communications through these huge antennas, and then when they turned it on, they were having this background noise all the time. And they were like, oh, what is this? We want to have communication. So they went up into the antenna and they found some pigeons. And they were like, the pigeons. So they flew away the pigeons. There's like I've heard debated stories about how they did it, but they did it. And then they went down and they were like, okay, now it's gonna work. They turned it on and the signal was still there. And just a few miles away in the university, there was a whole group of astronomers or physicists at the time debating of, hey, if we compress the universe, we should expect that light, and that light should be in the microwave. So this was this amazing coincidence that a few miles from them, they were already trying to measure the signal. And from what I've read, also there was a Soviet Union group that was also in this theory side thinking that this was gonna be observed. So, sometimes you find the cosmic microwave background, or, oh my God, I didn't want to say that word until now, but this amazing light emitted by the early universe. But if you see, like, this is pretty boring. It's just like flat and a line in the middle, considering this is a really important thing for cosmology. So back in the 90s, people started to develop better telescopes to measure this, and in the 90s, they sent this COBE mission to space that started to find, okay, again, the Milky Way in the middle, but that slightly temperature fluctuations. Then there were better measurements until 2015. So what you're seeing here is that similar to when you have your phone and you go to Instagram and you take a selfie and you want to increase saturation and you want to maybe get more flourished, there's this parameter, you increase the saturation, We do the same here. If we increase the saturation, we start to find these little details. And as I said, I don't care about the Milky Way, so we take it out, and voila. This is the first light ever emitted by our universe. It's not light coming from stars. It's not light, or from the fusion of stars. It's not coming from objects as you usually, observe in telescopes, but from the early glow of the universe. And as I said, we take out the Milky Way and we found this. We call it the cosmic microwave background. Cosmic is because it comes from the cosmos. Microwave because we detect it in the microwave regime. Background because it's in the background of everything. It's coming from all over, all directions, and it's really, 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 really smooth. If you measure the average temperature of this, is, as I said, a few Kelvin. So it's really, really low temperature. And it's just amazing. If you just go to Yosemite and if you were able to observe microwave, you will see something like this. This is a video I made a few years ago. It would be really different from what you're used to, right? Like there's no evident galaxies out there. It's mainly these like red and blue dots, and I'll be explaining in a second why we observe that. I'm gonna tell you some fun facts about this cosmic microwave background radiation, or as people call it usually in this field, CMB. So the CMB has really interesting physical information. One is that it fills almost the entire observable universe in a really homogeneous way. So as I said, you only see these tiny variations if you really, really, really increase the contrast. And the fact that it's homogeneous, it is telling us that if we compress the universe in every direction, everything more or less was the same. Like if I go back to this image, there's no big, like imagine we find like a really red blob here. That'll make our universe completely different. And this is telling us that this idea of a universe that is expanding makes sense. So this is actually one way of proving that the universe expands. Not only by the fact of observing galaxies, but the fact that the same exercise I did before with you all. Another thing is that I told you about this calculation of, compressing the universe, but I didn't tell you more or less times or which epoch we would do that. So the universe, we estimate that it has 13.8 billion years. And this light was approximately emitted when it was 380,000 years old. So this is really, really early universe, and almost the earliest we can reach. We can talk more about that. There are some theories on how we can reach earlier epochs. Another thing, well, I already mentioned it, is the fundamental evidence to support this theory of the Big Bang. So the Big Bang, it's misleading because it sounds like an explosion. In theory, when a cosmologist or someone that works with the cosmos is talking about Big Bang, they mean all what I just explained to you. It's hot Big Bang is the fact that everything was more compressed and it was hot. So that's why this could mislead to confusion, because we're not talking about an explosion, we're talking about everything more compressed and hot. Okay, this is the most, I think, exciting part, and I know it's a lot of text, no worries, this is the only really long slide text is, I showed you redder and bluer dots. I'm gonna just go back for a second. So, yeah. So there are redder dots and bluer dots. Those corresponds to photons or particles of light that have higher or lower temperature. And these differences are really, really tiny. These are like 0.00002 degrees difference. So this is really increasing the saturation. And again, this is why we believe the universe is really homogeneous. And you might ask why there's these tiny fluctuations. And the reason is because some of these particles interacted before they left whatever, this cosmic soup that, imagine we're putting everything together, compress it, everything was interacting, and we're literally having particles being ejected from areas that had like higher potential wells, like if these particles wanted to escape, they had to give up more energy, or they gain energy when they came to us. That's why this supports this idea of a early universe. And wherever we find these dots, this tells us about the universe. And I'm gonna give you one example in a second. So these are different realizations. If I go to my computer and as I said, we know the theory of this, and we try to describe this, and we compute maps of what we would believe would be the CMB. We can have, for example, this realization, this other one, and this other one. And this one have 3 different assumptions. In the universe, we can talk about curvature. When you're in Earth and you go to the South Pole, and you meet a penguin, and then you say, okay, goodbye to the penguin, and you go in opposite directions. Eventually, if you walk really far and whatever, you find your way through water, you can find with the penguin again in the North Pole. And that's because we live in an Earth that has, in a surface that has some curvature. Similarly, the universe can also, in theory, have a curvature such that if you're a particle and you're getting away from other particles from the CMB, you might find themselves again, or never again. This would be a flat universe, because there's no curvature, or there's positive, negative, and 0 curvature. And I always say, flat universe, not flat Earth. Important. But yeah, so the cool thing is that we can learn about, the geometry of the universe just by seeing these dots. And what we found is that the universe is flat, not Earth, okay? But you're a really knowledgeable audience, I don't have to explain that. Okay, but the fun stuff. Why am I here? All what I showed you is not state of the art. These are things people have been studying in the last, I would say, 30 years. I mean, if I go back, this really nice image by the Planck telescope was observed in 2015. So things have, changed in the last 11 years. And I would argue one of the most important things is that we need better resolution for doing science. So if we zoom into a particular, make a cutout of my map and zoom in, you'll see there's some pixels, of course, because this is an image. Same as you do with your images, but now with microwave images. And we would like to have better resolution. We need bigger microwave telescopes. Everyone wants bigger telescopes. But they're not easy to build or to have in Earth. So in theory, we can launch more satellites, but we really, it's a challenge to make them bigger and in space, so we can do them in Earth. Here I'm showing the atmospheric opacity at different wavelengths. As you know, gamma rays, X-rays, we can't observe them. Our atmosphere blocks that. We know that we can observe visible light because we're seeing each other. We see the sun. There's some wavelengths we can't observe, but microwaves and radio are in this sweet spot, right? We can observe radio really well, but microwave is like, yes, no, yes, no. We can just go to a hill. The reason why it's hard to observe microwave, as I said, is the same thing with your microwave at home. There's water vapor in the atmosphere. So similar to your microwave, your pizza is really bad. Well, your light from the cosmic microwave background is just interacting with water in the atmosphere. So we need to go to high altitude, really high altitude. And of course we go to the best country in the world, Chile. Dun, dun. Chile has an amazing desert. The Atacama Desert is really, really, really high. We call it altiplano, because it's really high and plain. And Chile has a lot of telescopes. The north of Chile is really long, really vast. All of this corresponds more or less to the desert. If you have been, it changes, but the most dry parts corresponds to here. And I need to advertise my country. We host more than 50% of the ground-based telescopes of the world because of this amazing landscape. Some of them are under construction, some of them are complete. And I will continue talking about Chile a bit. Here I'm showing, I'm showing the tree map of exports. We export a lot of copper and other things, but the most important thing we have ever exported, in particular to the US, is Pedro Pascal. So if you didn't know who's Pedro Pascal, you should, because he lives here. He's from the US and from Chile. This is an AI image. He has not, I tried to make him visit the telescopes. He's a Hollywood actor. He acted as the Mandalorian. I'm not a fan of those movies, but he's Chilean, so we just, we're happy. So Chile has telescopes, and we also have Pedro Pascal. So from now on, I'm gonna use Pedro Pascal as a scale for my telescopes. So if you go to Chile, you can go to really high altitude, and in particular, you can go to an area called the Llano de Chacnantor, which has a lot of radio and micro telescopes. And in particular, here you can see what was the Atacama Cosmology Telescope, Atacama because of the desert, which was a micro telescope from the ACT, that's the acronym from the Atacama Cosmology Telescope, collaboration located in Cerro Toco Hill, in the Antofagasta region. And it's really close to Alma, if you have ever heard of Alma. Alma's more popular, so, and it was located at an altitude of 5,000, more than 5,000 meters over the level of the sea. Can anyone help me with feet in this one? This one is important. 60,000?
66.
Okay, 16,000, yeah. So it's really high. If you go here, you'll have half of the oxygen than here. So you need to go usually with oxygen tanks. And this is Pedro Pascal for reference. So they're really, really big. And if I can zoom in, this is how they look. I went to recently renew my visa, and I took those weeks to visit these telescopes. And there's no telescope inside because they decommissioned it, but the shield is still there, and it's pretty big. This is Pedro Pascal for reference again. And as I said, this was an amazing telescope. It was a survey, so it was observing the sky for, I think it was 6 years, non-stop. Well, of course, stop if there's things that push it to stop. But as almost every night that we could, and during day. That's another thing. I don't know if you knew, but you can observe microwave and radio throughout the day too. You have to avoid the sun, but. So yeah, observing through night and day, and this is the improvement you'll get if you go there. So this is Planck, as I said, if you go to space. And if you go to Earth and you combine this with ACT, you get all this information, and you start to see these dots. And you say, wait a minute, what are those dots? Before I tell you, we find a really great improvement in resolution. And this is the final map that the Atacama Cosmology Telescope made. So it's not the whole sky, because again, this is not from space, we're in Earth, so we're limited to half of the sky approximately. And this is another way of plotting it, but this thing is the Milky Way. So there are different ways you can put this map. But the resolution, as I said, is amazing. And as I said, there are all these little dots. Some of them are more red, some of them are more blue. Those are harder to see. But this is state of the art. And they're standing completely those dots. And those dots are actually galaxies that are in our foreground with respect to the cosmic microwave background. So if this is the cosmic microwave background traveling, through the universe to reach us, it has to travel through all these galaxies, quasars that are, this is a type of galaxy with a black hole in the middle emitting a lot of light, but also galaxies and then reaching us. And that's where Pedro Pascal is. But it has to go through all these galaxies, and some of them will interact with these galaxies. So again, I'll go back to this plot that I showed of the history of the universe. We had the early epoch, we had an inflation. That's why we have this thingy here that a lot of people are like, why did they have that? And then darkness and the first stars and galaxies now. The CMB photons, or the CMB, has to travel through this stuff to reach us. But it does not travel just in a straight line. it can suffer, it can get deflected, or it could scatter out with particles. And as I said, it doesn't travel necessarily in a straight line, and we call that CMB lensing. I don't know if you have heard of lensing in the context of galaxies that are in the background of other galaxies, but you also have this effect with microwave. And in particular, this is a simulation of how the CMB changes when you have a lens like all these galaxies in the middle. It's really slight and not a big effect. But this is literally, if we see a big or a small change, this is telling us how much matter we have in the universe such that it has deflected the light or not. So it's really, really, really interesting. It's like trying to understand what is causing this crazy lens. Of course, this is an exaggeration, but trying to understand the mass of the source of whatever is the object that has that is in charge of this lens. Another effect is the fact that these particles of light interact with other particles. So, for example, if you have a big cluster of galaxies that has a lot of gas, really hot, your particles will gain some energy if they interact with these other particles. And therefore, you end up with higher frequencies. And so, in other words, the interaction of this light with free hot electrons, that's what I mean by particles, in these galaxies leave an imprint on the observed CMB map. And some of them were these little holes that I was telling you. So we're able to study galaxies by backlighting them using the CMB as a backlight. That's why my title was called like that. But also, not only because these clusters or galaxies can be hot, this might leave an imprint. Also, if these particles are moving and you have a CMB photon, remember CMB photons are going everywhere, so they are not necessarily always pointing toward my telescope. They can be horizontal here. If this cluster is moving away from me, feeling the interaction from another cluster that is moving towards me, that will also impact the temperature of the CMB photons, and usually in really small scales, and that's why we see this effect in really, really small scales. And in theory, this can help us to understand what is going on with these electrons that are part of these galaxies, and help us to understand galaxy evolution and formation of stars. So it's crazy, we can start to think about these things just by looking at the early light of our universe. So I'm going to show you some of the strongest detection to date. These are about to be outdated in a few weeks, but what we do is we localize where galaxies are in our CMB map, and we make cutouts. These signals, some of them can be really, really weak, so usually you stack on them, and if you do it, you get this effect in haze. And this is telling you where the gas of these galaxies are. And this actually work led by a colleague of mine, Henry, who's also in his PhD in Berkeley. And this is a thermal effect. This is because when these clusters are really, really hot, you get this effect. But if your clusters or galaxies are moving, you can also get this effect by including the velocities of these galaxies, and you can measure their gas too. And this is part of my PhD work. So it's really, really fun. That it's insane that we can study, if you think about it, the gas of galaxies by looking, at the early universe. I just find it unbelievable. This is what we have reached. And the future is bright because, we have a lot of galaxies and a lot of surveys coming on. But if you go back, let me just go back for a second to this image. One of the things you need to know a priori is where these galaxies are. I showed you that some of them are even easy to point when you just see the CMB map, but some of them are not easy to the eye, so you need to have, the stacks to get that signal. So you need to know where galaxies are, and that's great because we have telescopes like the Rubin Observatory or the Dark Energy Spectroscopic Instrument to do these measurements. So the Dark Energy Spectroscopic Instrument is an instrument that is located in the 4-meter telescope in the Mayan telescope at Kitt Peak, Arizona, Tucson. It's inside this huge building. If you ever visit, you should go and take a tour. They're really fun. And this is an amazing technology that is allowing astronomers to get the distance of galaxies with a really exquisite precision and make one of these maps like spanning billions of years. So it's really, really cool science you can do. And actually, let me just go back for a second. These measurements were done using those telescopes. We localized galaxies with that. And we use the Atacama Cosmology Telescope for that measurement too. So we cross-correlate telescopes. So when people ask me, what is your favorite telescope? I'm like, many. I need them for my science. I need more than one for my science. Another amazing telescope is the Rubin Observatory. You probably have heard of it. It's a telescope that is located in Chile. So this is Pedro Pascal for reference. It's huge. It's huge. This is located really near Cerro Tololo, if you have ever been to Chile. So it's near La Serena. So this is not the driest part of Chile. It's not that high, so you can actually go and you'll be fine. Unless you're really, really like out of shape, I think. But I think you should all be fine. And it has the largest camera ever built. And it's already working to produce a movie of the sky in this 10-year survey. And it's expected to observe, I think, 20 billion galaxies. So it's going to be huge increment of number of galaxies throughout these 10 years. And of course, I'm really excited because I can go to my CMB map and try to find this. But I also need better CMB maps because you saw the ACT or the Atacama Cosmology Telescope is not working anymore. But good news, we have more telescopes. I'm going to skip that for a second. This is a landscape of ground-based CMB experiments, as I told you. Of course, we would like to go to space, but with big telescopes. So right now, it's better to go through in Earth. Some of them have the Chilean flag because they're Chile. But some of them are in the South Pole, and South Pole is also really dry because it's cold. And they can also have amazing observations. And I think you are going to have a talk by someone working on the South Pole telescope. So it's really cool science. And they're going to be talking also about similar stuff, maybe with a different perspective, but really, really interesting science. The political landscape is a bit hectic, so there's some telescopes that are not going to be anymore in the landscape. But the one that is exciting a lot of cosmologists is the Simons Observatory. And that one is just next to where ACT was. So the Simons Observatory is a complex of 7 telescopes. This is the Large Aperture Telescope that is making a huge map of the sky. It started operating almost at the same time as Rubin. This is Pedro Pascal for reference. And it's also at really high altitude, and it's going to produce a map that is even better than the one we currently have also in a couple of years of survey. So it's really exciting science for people that do the kind of science I do. So as I said, we can learn about galaxies and their process of formation, because cool thing about this background is that given that it's at the edge of the universe, it can interact with anything that we have. We don't have to, when people do the same, weak lensing or other ways of studying galaxies that are closer to us, they need galaxies in the background. We don't need galaxies in the background, we just have everything. So it's really, really cool science you can do. I just also wanted to show you how the sky looks when you switch from visible light to microwave. It's completely different. And you can see a galaxy here in the middle that is also emitting light in the microwave, and that's why you can see it in both. So, it's really amazing that we have reached a point that we can study the universe as such different wavelengths in a vast area. So I'm gonna finish now and say thank you so much for allowing me to talk about this topic. This is, as I said, state of the art. That's why I didn't talk much about, usually people talk about the origin of the universe, the CMB in really detail, but I thought, it would be nice also to hear what is people currently working on. And there's a lot of challenges because, we're working with real data and there's systematics that we need to address, but it's really, really exciting. And yeah, More than happy to take your questions, and thank you so much for having me.
Questions?
Why is it we only can observe up to 380,000 years?
Sorry, I'm drinking water. Let me just get it, because I get it for Zoom also. Or for the recording. Yeah, so the question is how it come that we can only observe up until the universe was 380,000 years old and not before. So if we continue with this idea of compressing the universe and going to even higher temperatures, the reason why we have light is because you have protons, electrons, and then light bouncing them, and then the temperatures, and also, sorry, neutron, oh my god, I've been coding the whole day, sorry. Hydrogen. So once you lower temperatures, you allow, because if it's really hot, protons and electrons cannot bound into a hydrogen. So once you have this, you have light bouncing mainly these electrons. But when you lower temperatures down, this hydrogen will be created, and then this light will be free to travel. If you go to even higher temperatures, you would not even have protons, you'll have quarks. And light will still be, bouncing all over these particles. So you need to lower temperatures such that the light is free to travel and it's not gonna find an electron. In theory, you can use neutrinos. Neutrinos are really like other type of particle, they're really, really, really light. And these decouple from this cosmic soup earlier. So there's some theories that you can observe this neutrino cosmic background, or cosmic neutrino background, but it's really, really hard to detect. And there's some people working on that. If you do that, you will really get to earlier epochs of the universe. So that's one way. Another way is to use gravitational waves from the early universe. As we use light to observe. You can try to use gravitational waves to hear or see. It's a different way of seeing, but you know what I mean. How the universe was at the beginning. But yeah, it's just because light is trapped, like bouncing in particles. That's a good question. Yes?
Yeah. How come they're finding galaxies close to the edge of the universe? We would expect that they wouldn't be full galaxies.
So the question, if I understood, is related to the early galaxies. So maybe I can go back to one of these images. Give me 1 second, that one. So, we know that like the edge of what we can observe right now with, telescopes is the cosmic microwave background. And, the question is, when can we find the first galaxies? That's an open question. And James Webb is helping us to study that. James Webb is a space telescope that was launched in 2021, and it has, bring a lot of challenges to understand how the first galaxies formed. That's still an open question. If I also go back to this image, what happens here is also a mystery, and now we're starting to understand when did the first galaxies form, first stars. Did these stars collapse in huge, massive black holes? People are starting to find these called red dots. I'm not an expert on that field, but I know that's already like questioning, because if we start to find galaxies, this is like, we think we're gonna find them here, but then if we start to find galaxies here, all our cosmological theory has to be able to explain that. Or maybe the way we believe galaxies and star form is wrong. And that could be. So if you think about it, we have a static image of the universe at every slice here, because light has traveled. And that's why what I work on is also helping to understand that, because the gas is really important. The only way you can form stars is that if you have gas collapsing. So that's why we do also care about these galaxies, and that's why it's attractive to use the CMB, because because the CMB can somehow know what happened here, either if it's before or afterwards. So everything is complementary, and it's like really state of the art. And yeah, so astronomers are gonna have a job to do in the coming decades to answer those questions.
I was just curious, you mentioned Chile has, over 50% of the telescopes. Is it just the topography of the country that led to that, or are there other things that are kind of reasons for that?
Yeah, so the question is why Chile has so many telescopes, I would say. Well, we're really cool. No, it's a mix of things. So the sky you see from north and south hemisphere is different. So even if you put a telescope in the north, that's also gonna see different parts of the sky. One thing is that if you see a world map, there are not many countries in the south hemisphere. Yeah, so there's only a few. So this is the equator. Yeah, South America has a bunch of countries, but then you have only a few here, and then a few here too. So most of the population live in the north hemisphere. So one of this is the desert. This telescope started to be built in massive production in the 60s. We had some telescopes before. The first ones were 1880s, when people were trying to study the motion of the solar system, and they needed to have also stars in the south hemisphere because they need the whole sky. So that's one thing. If you want the whole sky, you either put one in the north and in the south, and there are not many that countries. Chile is really dry. You need to have dry places, hopefully high. So that limits already the countries you can put. Also, if you already have telescopes, it's even easier to build more. Because then you have the roads, you have the agreements, international agreements. If you're an astronomer in Chile, usually, depends on the telescope, but you have exclusive access to observing time. So that makes it really attractive. And we have a lot. I mean, this is a bunch, and these are all on the same site, not because of a coincidence, it's because they're managed by the same organizations. And also Chile has shown to be a stable country, even though we have had a dictatorship for 17 years, the telescopes were operating as normal, and that gives a lot of political stability. There are other countries that can potentially host CMB telescopes. One of them is Pakistan here, and that area is conflictive. And I know there's some groups trying to put a telescope in Tibet. That's how we call it in Spanish, but you know what I mean. But that's also challenging because of political reasons. So it's a mix of things. South Pole is also hard. I mean, it's not trivial to have a telescope built there. It's easier to send someone to build a telescope, to fix whatever, imagine something broke to Chile, than to the South Pole, where you have to usually go to New Zealand first and then go down. So it's a mix of things, and yeah, so it's good that we have all those conditions to guarantee that. And also dark skies, which it's a bit challenging because everywhere in the world we're suffering of light pollution, even in Chile. And if you have a desert, you have less cities. If I show again this map, there's only a few cities here. There's one here in Arica, one here in Antofagasta. It's mainly a desert, so it's really dark. But if I have the time later, I'm more than happy to talk about this more. But light pollution is, I would argue, the most worrying thing everywhere in the world, not only Chile.
I think one of the slides you showed, some of the cosmic microwave light hitting some galaxies and then refracting off of them and moving towards us. And you used those to explain those spots that we saw in the background. And I guess my question was how do you distinguish? Yeah, this light. How do you distinguish light that what came from the cosmic microwave background and refracted through a galaxy versus light that the galaxy just emitted? Are these galaxies not emitting microwave light?
You caught me. Okay, the question is well, you're turning a telescope. I'm gonna rephrase it, but you're turning a telescope. You're receiving everything that is in microwave. Indeed, you're having some microwave light that is bounce and whatever, but also you have galaxies emitting. Yes, and that's a challenge. There's ways you can mitigate. The CMB has a really specific frequency. It's a black body. radiation. So you know how it, you know the frequency dependence. It peaks at certain frequency at 220 gigahertz. So what you can do in your telescope is that in the Simons. So this telescope has in the detector you have different like tubes that are sensitive to different frequencies. So slight different frequencies from the CMB peak. And if indeed these galaxies are emitting some light, they're not going to have the same frequency emission as the CMB. So in an ideal world, you want to have a telescope with different frequencies and as much frequencies as you can. It's a challenge because the higher, let me think. The lower frequency you can have, the higher frequency, it's hard to observe from Earth. So you have a lot of challenges, and people use the information from different frequencies to get rid of that, but it's really challenging. And actually, my colleague Henry was having a really hard time to get this signal, the one I was showing, this one. I didn't show you if you go to the original paper, you will see the same signal, but with a dot in the middle, like blue, and that's the emission of the galaxy. We call it the cosmic infrared background. So it's also a background light, but like from the galaxies themselves. There's other emission here mixed, but this is an outreach talk. So I'm not gonna be talking about the details, but yes, you get everything. But that's also fun, it's like trying to disentangle what are you observing. The problem is when you think you got it and then you have dust. There's a lot of dust, riding out there in the universe.
So these patterns of gas that are in these galaxies, are those absorbing the microwave CMB, or is this refracting the CMB, or is this something? What are those photons?
So here in the left, the question is, what is this? Kind of. So first, if I have to show you a galaxy, it's the size of a pixel. So this is really extended. So this is tracing the pressure of the electrons that are part of all these galaxies that is stacked on. And what happens is that you get the CMB photons and they change slightly their frequency. And then that change of frequency because of this interaction, they, for example, gain energy from these hot electrons. That's why you get a tiny fluctuation of temperature, and then you stack and you get the signal. My measurement is a bit different because I am trying to use the velocities of these galaxies, and that helped me to mitigate the contamination. Actually, that's why I use it. When you do this, you don't get the emission of the galaxy themselves because you're weighting by velocities that are whatever, positive and negative, and you get rid of whatever is positive emitting, I would say. And this is actually tracing the gas. So this is tracing the pressure of that gas, and this is tracing the gas. And okay, you might say this is just a blob, Bernie. Why are you so excited about this? It is really interesting because if a galaxy is just a little point here, and I'm finding that the gas is much more extended than that galaxy, that means there's something pushing gas outside of this galaxy, and that's potentially a black hole in the middle, putting everything out. I hope that explained a bit more okay, cool.
All right, certainly want to leave time afterwards if you want to speak to her personally and ask more questions, but I thought this is fantastic, so.
Thank you. I don't know what it is.
And you had mentioned our speaker coming up in 2 months, and she's right, it's Dr. Clara Vergas. We'll be talking about their measurements of CMB from Antarctica. So now that you have the background, you'll be better prepared for that lecture.
Yeah,
so,
thank you. I know it's a complicated topic. I'm still confused, it's a whole PhD, but it's really, really interesting. And as I said, this is going to be the future of this science. So, the CMB is still out there and is teaching us not only about the origin of the universe, but also everything that is happening after it was emitted. So thank you so much for allowing me to speak about this. Hope everyone knew about Pedro Pascal. That was the joke I was telling you.
Oh, yes, yeah, I certainly remember that. That was great. I honestly didn't know who he was. I mean, certainly